Shame that Christian couldn't make it. I'm sure if he was here yesterday, we could have convinced him to sit and play some keyboard. Anyway, and Jesse was not there yet as well. I mean, he could have played as well. Anyway, so this talk, I gave it as a lecture at Technical University of Vienna about a year ago or so, after giving another course there on asynchronous design. So perhaps I could have introduced you more into the ways how asynchronous circuits are designed and used, but that's probably for another keynote, maybe sometime. So this talk is essentially, I called it data-driven computing, and there is a subtitle here, Liberating Computing from Memory Walls. And what I'm going to discuss with you, it's very much a position talk that you may look at Zetland machine not as a mechanism to do things like AI or machine learning per se. I mean, we will talk about learning, definitely. We'll talk about machine learning, we'll talk about training, but not perhaps very much in the context of AI, but rather in the context of design automation. What do we get from learning? Is there a way to use Zetland machine, for example, effectively as a compiler to build efficient systems, particularly efficient circuits, efficient hardware? And I put it in the context that where is one of the big challenges? The big challenges come these days, and for probably a long time already. They come from the so-called memory wall. And before I talk about this memory wall, is that this is the conventional way how we see computing, which starts with the idea of an algorithm. Nice Greek word. Ancient Greeks invented the idea of algorithm because they wanted to do some sort of computations. Even Pythagoras, for example, had some sort of algorithm there, or Eratosthenes' sieve. We know all these things. And algorithms are supposed to be sufficiently general. They're supposed to work for some kind of large species of data, effectively. And as we heard from Ole Christopher yesterday, that he said it was very interesting sort of antithesis between being generalist and being specialist, like doctors. So doctors can be generalists. In many ways, this traditional way of computing is, with algorithm-driven approach, is very much generalist here. So we have an algorithm in programming language. We've got programming language grammar rules. We pass this algorithm through a compiler. We get the machine code, and this machine code sits next to the CPU, and it has to be providing instructions, instruction after instruction. So CPU fetches these instructions. And obviously, I also should have mentioned this ISA instruction, so set architecture specification, which gives us the way how to generate the executable code or object code or executable code. So that's the traditional. Now, the problems with conventional computing, which can be quickly sketched here, is that conventional computing is heavily based on the paradigm which is attributed with John von Neumann, which is the paradigm of stored program and instruction-based fetch execute cycle. So memory here, which provides instructions, is sitting on the critical path. And inevitable that this memory becomes a bottleneck. However ingenious this idea is, in modern age, when we need to do some computations with a very fast rate of data, for example, that arrives from the input channels, fetching instructions to process this data, it could be quite a bottleneck. And this is the architecture of one of the sort of classical processes that you'll find in textbooks, DXL, I think it's probably. So you've got this 5-stage pipeline. And here on the left, you see memory where you fetch instructions. The IF is the stage instruction fetch. And if memory test. Dominica is not with us. The fire warden. What would happen? Right. So I'm not inviting you to kind of run exemplars of instructions through this pipeline, but for many years we are still using these kind of processes. In fact, when Amulet, asynchronous version of one of the earliest architectures for ARM, that was based on sort of similar kind of pipeline. And as we can see, so we have this bottleneck here. So how to mitigate? There are obviously there have been ages of ways of mitigating this von Neumann bottleneck. So, for example, use cache between CPU and the main memory. Use separate caches, separate access paths to data and instructions. The so-called modified Harvard architecture. Use branch predictor algorithms and logic. Use limited CPU on chip scratch pads. Implement CPU and memory hierarchy as SOC. So you've got actually memories, not just one long access memory, but much faster memories. And you kind of use the locality of reference and reduce latency, increase throughput between CPU registers and main memory. But fundamentally, it still remains a control-driven processing. The programming is based on encoding the order of execution of the computational operators explicitly. So even if we change the program from imperative languages, remember this kind of algorithm of algorithms, sort of you've got programming language, say, if you even change this programming language, say from C++ to say functional, say Haskell, for example, we basically still use the same architecture for that. So we may need more radical approaches. Now the question, why don't we just move from the so-called control flow to data flow? And that's been quite successfully used by some companies. In fact, not just academic lecturers who talk about control flow versus data flow paradigms. But here is the kind of very schematic sort of capture here of what is control flow on the left and what is the data flow. So instead of processing instruction through the stages of the instruction pipeline, where somewhere you've got also access to data in and out, what you do is that you run data and you've got some sort of function stack, and these function tokens, they propagate to all stages of this data pipeline, and they tell each stage of this data pipeline what kind of function is supposed to be executed there. So this is already quite a big step. And there is a company called Maxilla, which is quite successful in accelerating various computations, particularly for the financial services, all kinds of financial. And in fact, our friend Wayne Luke is one of the founders of this company. They basically maximally exploited the idea of non-von Neumann approach, where data flow, as you can see on the right, data flow was spread between cores. There is a potential for massive parallelism here, obviously, because each core gets something in terms of data. And you also have configuration. And here is the word configuration, which is quite important for us to start thinking a little bit more about it. As you can see, there's programming language, say from C, C++, Fortran, changes to Java. So you've got a compiler. Somehow you get parallelized Java into some kind of elementary, not threads even, so tokens that go. And so the only thing that goes from memory and into memory is data here, right? So you don't have instructions on the bottleneck. So another way of completely sort of swing from the programming style, trying to get rid of memory that has to be fetched for instructions, is why don't we just synthesize hardware logic? And this is what we've been doing, synchronous or asynchronous, and those who did IC design or even digital design would probably know what is RTL synthesis is. So basically synthesize hardware logic. And so designing ASIC, for example, hardware logic synthesis, we start with an algorithm, but we start with an algorithm. That's one of those things that still prevails in our heads. Then we develop a data flow graph out of this. Then we perform high-level synthesis for this data flow graph. So we generate the behavioral RTL from there. So then we, at this RTL abbreviation is actually register transfer language. So we talk about register level. And between registers, we've got logic. So it's pretty much low level. So it's in a way, it's analog of the executable file, as you may see, in the hardware synthesis. So we perform logic synthesis, we basically synthesize logic. We've got the net list of gates, and then we map this net list to logic cells. Then we do place and route to produce a layout for an ASIC. We send this file then to for fabrication. Now we may see, okay, well, some of these things may be too expensive. We may do something cheaper. We may have already something which is called FPGA, field programmable gate array. And this flow for field programmable gate arrays, so we don't fabricate, actually, we don't send the file for fabrication. We already can map logic cells into some sort of configuration file of our FPGA. But remember that we start with the algorithm. We have to be generalist still. So in FPGA, this flow would be a bit different after RTL, but fundamentally the same. So hence accelerators are often built in FPGAs. And this is probably the fastest possible design without program memory on the critical path. And the problem is that it's too application specific becomes. However, there is this generalist algorithm. So interesting, already one step towards maybe the things where we can start doing some kind of compilation by learning. So FPGA allows programmability, but not on the fly here. So can we somehow find some kind of sweet spot still? So we may still want a programmable process. We may continue to program algorithms. I move from control flow, data flow. Still, the program will sit in memory, and we need to fetch instructions, so instruction tokens, and of course, fetch and write back. So that's programmable. That's not hardware synthesis, as we've just looked at. We can, however, selectively accelerate some operations in special purpose hardware blocks. And some people do it quite effectively. So in the last bullet point, I refer here to one such approach. So if we know exactly what they need to do, these accelerators can be mapped into FPGAs or special purpose hardware sitting next to the general purpose. So that's why some people start saying, okay, you can put an accelerator for as some special type of instruction which will be programmed still within the overall cortex of, say, RISC-V or Cortex M 0, for example, ARM processor. But if it's extendable, MIPS used to have quite a bit of potential for extendable instructions. So then for that, you have special purpose hardware access. And this is the approach called evolutionary approach by Ismail Zadeh from the States some time ago. I will show you some couple of diagrams from his approach later. But now, well, let's forget about algorithm-based design. Let's shape computing according to process data. So we are not generalists. We are swinging to becoming specialists. And in fact, specialists not in terms of the special purpose algorithm, but actually the data. We don't know even the algorithm. We just have data. And for simplicity, I will be referring to the scenario of the labeled data. So I'm not going to talk very much about things like my brain is not working too well. Jesse, what kind of learning you use? Regression. I'm not going to talk about very much about regression type of thing, but regression could also be put under this kind of wrapping. But mostly we'll be talking about labeled supervised learning here. So basically, another way is to swing to a different programming paradigm, data-driven or scenario-driven. So we basically have to play into our machine, into our effectively compiler. We will be playing in scenarios. This is what is going on, and this is what we label it with. And input, output combination. So here we have no mathematical or algorithmic model of computation initially, but we have data mappings between inputs and outputs. So we avoid step-by-step micromanaged execution of the detailed plan stored in memory. And if those mappings are in the form of truth tables, we can try to mimic high-level or logic synthesis, a bit like ASIC and FPGA design. So we've got effectively some kind of truth tables. And I will, show one of those examples that Ole showed, MNIST, what else? So hardware fabric is, however, because we want to retain some kind of programmability, so we are not re-synthesizing and not refabricating everything. So hardware fabric, however, has to be prefabricated maximally. And we produced some sort of configuration code from our program code. So our program code is those truth tables. Configuration code is something, you're probably guessing what it will be in the context of settling machine, but I will not say that. So, but the question is that where is the catch? Right, well, the catch, always there, is that instead of detailed plan of action or specific algorithm in the programmer's head, we have to invest our time into collecting data about what we want to do. So we are not inventing an algorithm that will be maximally general, but we are supposed to collect data and probably curate this data. And this is not an easy process, as we saw from yesterday's sometimes presentations. Well, Jesse talked about the EIS, that sort of data. Well, that data does not give quite a significant win for, say, Zetland machines or some other methods. So we want maybe really acceleration, maybe in the real-time context. So we have to perhaps see how maybe we collect data. So the data might need to require some other elements. And so the programming is actually dataing. And that's essentially leads us to synthesizing the compute engine for this particular task. But it has to be still programmable maximally, because we don't want to completely build the new ASIC necessarily for that sort of thing. So the question is that where then should we have memory? So memory is no longer sitting in the form of instructions. We are not going to fetch instructions in the von Neumann style from memory, but the memory, and ideally to speed up by say 1000x. So we have to reduce the access rate by that particular factor. So we should ideally access memory orders of magnitude less frequent than any elementary computation operation. So the analogy a little bit with the neuromorphic operation. So imagine that neuromorphic. So memory actually in our brains is in chemistry. It's not in the electrical part. It's sitting in our chemistry. As a result of accumulation of knowledge, and our learning training is actually compilation. So we compile, and we have these chemical deposits somewhere in our memory, all these connections. And but compute is in the physics, not in chemistry. So it must be fast and reactive then. So it's a bit like PID control, where integral is memory and PD are compute. So there could, of course, be some short-term, very short-term memory, such as some kind of storing some intermediate values in pipeline stages, so counting events. And if I had more time, I would have probably, oh, Johnny is here, yeah? Hi, Johnny. Remember we were talking about memory the other day, is that apparently even any AND logic gate has memory, because when you have to know when to compute AND. You have to have one operand and you have to have another operand. So if you need to wait for one of the operands when the first operand is already there, so the first operand has to be remembered somewhere. So we need some memory. That's why, you know, CMOS logic is fundamentally memory, not free of memory. So you have to, and towards the end of my talk today, I will talk about that electromagnetics actually gives us the chance to be truly memory free. So anyway, algorithm-driven computing, I propose to still maybe use similar kind of structure here of this kind of algorithm. So instead of algorithm in programming language, we have labeled or curated data set. Instead of grammar rules, we have data organization rules. Instead of ISA spec, we have some spec of our compute platform on which we are going to do processing. And instead of PL compiler, we've got a training engine. This is where we're going to put certain machine, in fact, to do this job. And then instead of machine instruction code, we're going to have configuration code. And instead of program-driven CPU, we're going to have inference engine. So inference engine will be our processor. And so here sort of several kind of principles, or I wouldn't call them principles, but sort of some statements here. Just mostly, you don't read everything, just read perhaps those things in red here. We don't want to spend too much time. So, but basically, we instead of storing in memory instructions, so only configuration of connections in the data path are stored, okay? Configuration of connections in the data path. So we store the configuration code of the problem-specific ALU. So this is effectively whatever, well, I call ALU. Effectively, it's some sort of inference. So inference block is tuned to the problem-specific data. So instead of traditional program code for the algorithm, we're going to have a problem defined in the form of a training code. So mapping between input features and output classification cases. And programming is essentially labeling and curating this data. The process of compilation to convert this training code into configuration code by means of learning. So compilation becomes a classification problem. And so compiler is a classifier of data plus reinforcer. So as a result, what we do, we effectively distill our ALU, our computation or inference, we distill it from memory. So memory access for writing is only during compilation. So we took it outside of the, and in fact, we download the configuration data to some registers acting as a railway points effectively. So memory is no longer on the critical path. And that's some kind of picture where having the idea of settling machine, we may think about this data-driven CPU architecture, where we have the inference logic here at the bottom, and we have the configuration compiler, and our executable code is effectively configuration code, and we've got settling automata that will sit in memory and provide us with this configuration code. So this memory is written during the process of compilation. Okay. And this is also kind of compilation that can be potentially, if we do partial learning, we kind of compile a little bit more if necessary, if the quality of the output is not as good as we want to achieve. So kind of modeling it, say, with Petrinets or some other behavioral model, you could see that in this loop here, which goes here, the speed is not obviously as much as you can do the speed of processing data. So if you can switch it from the execution, where the inference only waiting, and that will be even pipelined potentially, but then you can switch it into the learning mode, and then this cycle will determine your performance. So this is kind of a way of seeing the configure values that may consist of combinational and or sequential logic. In the specific case of vanilla settling machine, what we have is that we have AND gates. So we have AND gates followed by pop counts or CSUMs and max args and so on. But we may think about maybe some other fabric for computation. Imagine that you may even have the fabric of lookup tables. So you have lookup tables here from FPGA, and what you're doing is that instead of deriving configuration of the FPGA from your algorithm, you actually train it in your settling machine, which synthesizes the configuration code for your FPGA lookup tables from the data. Okay, so and one or the other way, I think things are moving in this direction. Things are moving in this direction in the evolution of what we see. People want to accelerate this flow of inference, that it can work with the either high throughput or also low latency. And towards the end, I will talk about ways of achieving very low latency, thanks to Adrian's work on self-timed implementation of this. But basically, these are the main building blocks: combinational sequential logic for LU, classifier is made of the threshold logic, configuration code stores linear tactic automata, and then reinforcer is hardware that has to produce penalties and rewards. Yes, Vladimir? Yeah, please interrupt me anytime.
So the data curation and labeling, is it supposed to be done manually by a human?
Well, it has to be automated. It has to be automated. We have to move to the automation of the curation as much as possible, because at the moment, this is becoming the engineering bottleneck. The time of engineers. Actually, I spoke to my sister a few months ago, who is in the project management for IT systems and banking. and she said that, oh, they incessantly hire graduates of the English language degree now, because what they do, they sit and curate documents massively, and highlighting different parts of speech there, so that these things can then be entered in much the same way like what you said yesterday about those documents, about the events happening.
But the point is that this is very time and resource consuming process. So,
but it's an interesting kind of job. I mean, they hire now language graduates of the language degrees rather than programmers.
so in algorithmic approach, you are in a way delegated to the algorithm, right?
Yeah. That's right. Please don't quote me as I'm saying that. I'm not saying that the era of algorithm design is over, but it's more like to say that, oh, there is another era coming that brings something else rather than era of algorithm design.
Have some kind of specialization.
Yes, specialization. Yeah. Yes, honey.
How do you prove properties about this sort of argument? An algorithm, you can break it down into steps. You know, it's old-fashioned. To prove the properties of correctness of a computation, an algorithmic approach is straightforward. Here, you're using data and reconfiguration, and it's a lot more flexible, and to my naive mind, it's highly communication orientated.
Yes.
But that flexibility makes the proof of correctness of the computation much harder.
I completely agree. We have to rethink the process of verification and proving correctness, and some of the things that probably that were not so pertinent or significant become more. Like Lay, for example, who proved that something converges. I mean, in the process of learning and training, we have to prove that we have data and we have the mechanism here that guarantees convergence. So we have to prove things like Markov processing, ergodicity, all these things. We have to prove them from what we have. So that's part of verification, I think, isn't it? So that we synthesizability effectively.
Also, to his point, one of the biggest things about algorithmic approach is they're not liable to change at all. So they're quite fixed in the approach. So whatever set of rules you've introduced are not liable to change. And in our kind of moving world, things change quite quickly. So the biggest advantage you get, I guess, with the data-driven approach is that also as your data changes, your model changes. So the way you learn changes, the way you adapt changes. And obviously then that comes back to the point again, as you move across, how do you keep proving this correctness? But
yes,
in any case of machine learning, correctness is something you need to not prove, but it's more reliability you're trying to prove. You're trying to prove that regardless of changes, we can consistently tell you this will give you not 100% accuracy, but close enough to a point where the ones where it's not, at least we could explain. And that's where this idea of explainability kicks in. As long as we can explain why it came to that suggestion, then maybe then it's not a case of correctness, it's more of, okay, but how or why did that thinking come into play?
Yeah.
But the biggest thing is, with algorithmic approaches, we're stuck to what you do until you change the algorithm. But with this data approach, as the data changes, everything changes. So you're not subject to having to re-implement the whole algorithm or re-implement the whole process again. It's more of a case of re-establishing how the model itself is changed. So I guess that's another thing.
Yes. I think it pushes us to some more incremental approach here, and this is what Ole said yesterday, that when we have some kind of new features maybe, and we, instead of just getting stuck somewhere, or examples that Steve showed that somehow you turn one animal into a completely different animal by just perturbing a little bit. So these are the things that we have to face here, and so there's plenty of work for formal methods, Annie. For formal methods people, even more than we used to have when we had beautifully algorithmized problems and formal. So Anyway, I'll hover over some slides here, and this is just to visualize a little bit. This is our kind of ideal input for logic synthesis. For years and years, we would use ideal input like this, and even in the framework of so-called approximate computing, we will have effectively this kind of input, and this is output. This is one of the items from the truth table. So this is one data item. And we can imagine that truth table will have lots and lots of these rows. Well, this is shown by rows and columns, but in the actual truth table, it's actually the entire row here, right? Which we call features and literals. And that's the code for the output. So it's handwritten digits. Ollie said that, okay, maybe certain things can be kind of marked here by noise, say 10% of cases. So we put some kind of don't cares effectively here in our truth table. And that becomes, but we can see it, approximate computing area. It's one of those areas that's been developing, as Richard would confirm probably for the last 20 years, quite a lot. And we ourselves did quite a bit in approximate computing. But in many ways, the approximate computing still was going in the traditional way. I mean, it will look at the architecture of the, say, multiply, adder, and we start to cut corners there and say, okay, well, instead of the proper XOR gate, we'll use this OR gate, which has less transistors, and we'll approximate for, and we'll see how it affects less significant digits and so on. But that approximate computing was still going not by learning process. Now we are in truly approximate world. We are training, because you can't imagine that for 784, I think, we've got the number of literals for the MNIST 28 by 28. We can't imagine 2 to the power 784 truth table like that. So we just have some snapshots. We've got scenarios. And on them, we have to do synthesis. So it's fundamentally approximate. So compilation by tuning is a new type of logic synthesis, effectively. We synthesize logic that performs according to these truth tables to the best of our ability. And possible optimization criteria here: accuracy, time, power, active area. So the logic synthesis by definition approximate, because our truth tables contain don't cares, noise, all kinds of stuff. This logic synthesis is based on clever tuning of the hardware fabric. And clearly this fabric needs memory. And at least in remembering the state of tuning Zetland automata. It may have some sort of internal memory, of course, in the inference engine, which I mentioned, like flip-flops for counting and shifting if we do things in the way that needs some sort of pipelining, maybe in the inference. So Zetland machine. Now this is something that I will hover, because the whole symposium is about Zetland machines. I'm sure that we all know a lot more, and that was the talk that I gave for people who absolutely were not initiated in Zetland machines. So it's a noisy XOR, a recognition, software simulation from Ole's paper. As you remember, we had lots and lots of literals, but we were trying to glean from this data that it was actually XOR between X1 and X2. Okay, and Stosif gave us very nice demo, bits and pieces yesterday, but if you want to really play with this demo, you can play. And here is the kind of stats there. What in the ALU, we use 20 AND clauses, potentially with 24 inputs in the classifier, 10 clauses to vote for, and 10 clauses to vote against. The classifier has threshold 15. Anatoly said that we should be more careful about having high thresholds. We should go for the rule of the square root of half of the clauses. So the configuration code is the product of clauses with inputs, 480 bits. Each bit is responsible for the link between literals and the clause. and each bit is a Zetlin automata. And that example from Ole's paper, the automaton had about 100 states. So after 200 epochs, the XO was learned with 99% of accuracy. And that's one of those introductions showing that, well, Zetlin machine is doing very well on this kind of non-linear type of data sets like XOR. So elementary building blocks, learning units. Here is this effectively small kind of unit which may be assembled then into the multitude, where we can have clauses and inputs. We've got small number of TAs. We've got some feedback blocks for each of these TAs. We've got random number generator here, and we can potentially tile this for this kind of tiling approach. We've had already some experiments how to tile, and I think Komal is now working on tiling quite a new way of tiling it with the much higher efficiency perhaps. So configuration codes from TAs arrive as includes. So we've got this simple configuration, simple netlists here with nonce and ors and ands. And obviously these ands, if there are too many inputs, then this will be tiled. And then it goes to summation threshold. Going to gradually use some of the pictures that I took from various papers of our group. And so that data-driven CPU architecture for learning and classification based on learning Zetlin automata here. So we have clauses module, we have summation threshold, we've got feedback, we've got TMs, TAs here, and these are some of the implementations which I plagiarized from Adrian's thesis. How to implement these things efficiently. Likewise, also this asynchronous way of looking at this, where we don't have clock. So we model everything with some kind of models, concurrency-based Petrinets. So you can see that we've got close computation. This is transition firing when you've got a feature and the partial close that produces partial close to the output, which will be picked up by another feature. Here we've got locally TAs, basically controlling whether this feature has to be included here or not included. And that's the tiling way. Could be nice kind of paper potentially for a Petrinet conference next year, wherever it is. And because I don't think that we have ever presented Zetlin at the Petrinet conference. I think people would really love it, especially those who work on synthesis of Petrinets. So, and here the data from Adrian's paper. So ASIC design for the learning unit, and now we use some of this data from this table to attract attention to potential customers of Minion. Sorry, guys. I'm mentioning Minion in passing. It should be the next TM symposium. We will have maybe a special presentation or demo. But these are the things that we are quite pleased to see, the way how we get the energy for inference and learning, training efficiency, tera operations per joule, quite substantial. And so none of these state-of-the-art, even for binary or binarized neural networks, they can do things with a similar sort of efficiency in terms of training. That's classification using learning automata comparison with neural networks of a self-timed settling machine. This is entirely taken from Adrian's work. So Adrian managed to get as much as 800 tera operations per joule in the async, which is almost 2 orders of magnitude better than synchronous, and training likewise. So as you can see, this is really very hopeful stuff. And so possible applications in computing. So I must be conscious about timing. So detection and classification of small patterns in data, sequences of events, or also known as microclassifiers, things like wake-up controllers, digital filters, also solving optimization problems, scheduling, routing, cache miss hit optimization maybe. So it can be put into some kind of learning, as I call it, commodized, commodity, treating learning as a commodity. You can sort of put these bits and pieces of little learning block that I showed you with some elements of inference and settling automata and feedback, can put it into. So, and training data may arrive in real time, and that probably third wave of AI, contextual adaptation, models to drive and explain decisions. Data for training may be issued on the fly in real time, and we need to build models by learning from it. So that's completely new type of things that we can't do these things in the cloud. It has to be online. And so, as I promised, Ismail Zadeh's approach called Parrot and NPU, as you can see, there is imperative source code, annotated source code, and this annotated, then it goes, some of the source code goes straight to the code generator, but some of these parts have to be accelerated. They go through getting data and learning, and then adding those things in the form of NPU configuration. So this is the way how these guys try to approach it. Parrot transformation. By comments, excessive interaction still between core and NPU may outweigh the benefits of using NPU. NPU is still memory heavy. Use of neural networks imposes demand to have inference engine to enhance specific reinforcement and weight mechanisms. And we can implement NPU using settling machine hardware and basically change this approach. And now a couple of slides about future directions of research and data-driven computing. So, and the way how to make machine learning a commodity. So memory-free computing. We don't have explicit states in our program, so we don't have states. Mind you, in the data, we don't have states. States are only in settling automata. And this is compilation process. So microclassifiers can generate almost unbounded number of control-related aspects and states automatically. So run applications multiple times and learn microclassifiers on the fly. They can be added to any application-specific logic. Memory to store configuration code can be multicast. And we are working on that. Multicast within memory, simple compute operations. And then something that we don't have. Do we have Tony today? Alex, have you seen Tony? That would be music to his ears because he's working on meta-surface and electromagnetic media that are ideal implementations for memory-free computing. And in terms of new type of programming based on scenario-based programming, that's also a potential. So a simple shortcut to programming would be by Python. It's already widely used language. And so we could develop compilers from Python to configuration code. I think we are doing that. An example of electromagnetic computing, spatial temporal meta-surface processor. As you can see here, for switching between spatial temporal operation, externally tunable, and this tuning is done offline. So this can be achieved using tunable active meta surface. 2D materials such as graphene, they can help doing these things, and people recently published papers about that. What they put here is that there is an FPGA which basically configures this meta surface in such a way that you compute that your compute elements here are something where you don't need memory. So edge detection, so differentiation, false spreading, you can have integration, and some of these things are done in our part of our wider group. It's not microsystems, it's done in physics. And Victor Pacheco-Peña, with whom we work, he is actively working on this spatial temporal meta-surface processing. Right, so I'm not bother you with references. And if you've got any questions still, I'm happy to answer, because the next session, I think, will be chaired by me anyway. So.
I think we should give a thank you, Alex Yakovlev. We have time for one or two short questions. Just to put things in perspective, 5 years back, just before COVID, there was a keynote I attended where the gentleman was basically saying that 10 years from then, people will have a laugh that we actually use latches in our circuits. Obviously, these days we do use latches because we want to hold the horse. Okay, before the signal, if you need two signals, you need to make sure that one of them is held back using latches so that the other signal can arrive in time. But he was making a point that, okay, in the future, latches will become obsolete because that stops us from being fast. That stops us from being, doing things at a speed that we can do our computation better. So any question from the audience? Yeah, Vladimir.
So thanks a lot. It was quite inspiring. So in general, I think you can introduce finer granularity in the computing, right? So we have imperative computing, we have declarative computing, where instead of how, we basically say what, and it shouldn't necessarily be explicit articulation of the algorithm, just essentially a set of axioms you should like to satisfy the conditions of the result, right? And then, yeah, data-driven computing, as you articulated it. So does it make sense to say that you are moving from purely procedural algorithmic approach to something which is highly declarative with no footprints of a procedural algorithm?
Well, the question, even with, thank you very much, Vladimir. We are in a way declarative, but still declarative depends how we map it eventually into the fabric, essentially, of which is computing fabric. So if our fabric is still based on certain things which are more traditional, like adders, multipliers, registered banks, and so on, we may be still pushed to something where we will have to have this computational stages, and we will have to give the control element, control information basically there, what they're supposed to do. So it's difficult to say. I mean, whether switching only to what is sufficient to completely optimize in terms of the having access to memory. So the key point is to find a way to effectively, what is the beauty of certain machines? Is that we try to train and accessing memory away from the process of computing. So all these hows and whats, potentially, they have to be taken outside the execution process, inference process. So that's why those watts, they have to be configured as well. So if we configure them in the process of compilation, that's a great thing. And as much as we can do it, but we need data. Effectively, we need data. Our what is in these data maps that we have to glean from the applications.
And we can often articulate those what's in terms of data.
Yes, we need to articulate those what's in data, and data may come incremental. And we sometimes suddenly realize that, oh, okay, we cater for a good set of classes, but actually some classes we can't recognize them, so we have, curate a bit more data there, so that we recognize it better. And but this memory thing, I think I pushed it very quickly through this towards the electromagnetics, is that we always have to remember that when we deal with CMOS logic, however fast it is, CMOS logic is based on the switch charge principle. And charge means that we have parasitic capacitance that we have to charge and discharge. And this is memory. And this is necessary even. We can't, in the CMOS, we have to live with this. So we have to mitigate sometimes these things, but we have to live. But this last few slides were about, we can move away even from that sort of memory, from the parasitic capacitances, if we know which what we do. So like differentiation, edge detection, this can be done on the fly in photonics with the speed of light, because we don't need even AND gate in CMOS, due to this parasitic capacity, it has memory to store one of the operands in the parasitic cap, because we don't have the other operand yet. So these are kind of things that go all the way down to what sort of computational fabric we use. But the main principle is that whatever fabric we use, we have to make most of it. And it's our belief that certainly in hardware is that certain machine gives us the chance to actually squeeze as much as possible of efficiency and performance, energy from CMOS logic, because CMOS logic is fundamentally rule-based at the level of transistors. And if our fabric will be electromagnetics at the surfaces, then we will try to squeeze maximum there. And there are always applications. Photonic counting, for example, where you talk about hundreds of gigabits.
Towards quantum computing, of course.
No, quantum. I'm trying not to touch it.
I think let's keep some excitement for the socials and during the lunch break. Thank you, Alex Yakovlev, once again. I think big hands for Alex again. Once again.
Thank you.